Hello friends, welcome back to my channel Chemistry Unplugged. In previous videos, we have discussed about organic reagents like LDA, Enamine, Wilkinson catalyst, PCC, mCPBA. Today we will discuss about problems related to these organic reagents, and we are discussing problems from CSIR NET and GATE. First question is from CSIR NET June 2011. In this question, we have to identify suitable reagent for the conversion of this compound to this one. So we can use peroxy acids or hydrogen peroxide NaOH for this reaction. But mCPBA attacks on electron-rich centers, while H2O2 NaOH attacks on electrons deficient center, and alpha beta unsaturated carbonyls are electron deficient in nature. So this reaction will be governed by H2O2 NaOH. Second question is, we have to identify the product of the reaction, and it shows strong absorption at 1765 centimeter inverse in IR spectrum. So in the first step, we will react it with PCC in DCM. So PCC is pyridine chlorochromate, and it will convert primary alcohol into aldehyde. First it will attack on primary alcohol, then it will convert it into aldehyde. Now we have a second alcohol group also, but it will not convert into ketone, but this reaction will undergo oxidative cyclization. We have also discussed about this in the previous video. So in this step, the lone pair of electron of oxygen will attack on carbon, and in the next step, this hydrogen will be removed and it will give its electron to oxygen. It is electron deficient, and this electron will shift here to form a double bond. So we have a lactone compound, and we know that lactone shows IR spectrum at 1765 or 1770 centimeter inverse. It is a characteristic absorption peak for lactones. Therefore, option D will be the correct answer. Next question is from December 2011 CSIR NET. In the first step, we will react cyclohexanone with Grignard reagent. So it will attack on the carbonyl group and convert this O into OH. In next step, we have para-toluene sulfonic acid, TSOH. So it will provide acidic medium, and H ions will be in the reaction mixture, and they will attack on OH to form H2O+. H2O is a good leaving group. It will be removed from this compound, and we have a carbocation, this plus charge on this carbon. So this bond will shift its electron to here to form a double bond, because it is a carbon atom which is electron deficient. So we have a alkene group here. This will be the compound A. So we have this in option A, C and D only. Then we react it with boron dimethyl sulfide. So it is basically hydroboration. In hydroboration, the BH2 group will attack on the less substituted alkene, and then it will be converted into OH group. We have also discussed about in previous video. So in the next step, we have pyridine chlorochromate. So pyridine chlorochromate will convert this secondary alcohol group into ketone. In next step, we have metachloroperoxybenzoic acid. So this lone pair of electron will attack on the carbon of carbonyl group, and this pair of electron will shift to oxygen. Then in next step, Baeyer-Villiger reaction. In Baeyer-Villiger reaction, tertiary carbon will migrate in preference to secondary carbon. We have also discussed it in previous video. So it will attack here, and this RCOO group will be removed from this compound. So we have this lactone here. So B will be this compound. So the correct answer is option A. In next question, we are first using lithium in liquid ammonia and tertiary butyl oxide. So it is a Birch reduction. In Birch reduction, if we have electron donating group in the compound, it will promote ortho-meta reduction. So after the ortho-meta reduction, one hydrogen atom is placed here, one is placed here. Okay, it is for methoxy group, this is ortho and this is meta. So it will be, this carbon will be reduced and this will. So we have this as compound A. So it is in the option C and B. In next step, we are using mCPBA. So it will undergo epoxidation. And because the mCPBA attacks on electron rich centers, so it will attack on orthomethoxy group. It is much electron donating than methyl group. It has lone pair of electrons on oxygen atom also. So the mCPBA will attack on this alkene group. So we have this as a compound B. So option B will be the correct answer. In next question, we are using cyclohexanone and a primary amine. So reaction of carbonyl group and primary amine leads to formation of Schiff's base. So it is a Schiff's base and then we react it with LDA. LDA will remove alpha hydrogen atom. So this is the alpha carbon atom and this hydrogen will be removed. So we have negative charge here. In next step, this negative charge can attack on the methyl group, and because of the presence of methoxy group, this methyl group will go below the plane. It will be attached in opposite direction to methoxy group to avoid steric hindrance. Then it will undergo ozonolysis. So this part will be removed by the oxygen atom. So we have option A as a correct answer. Then in the next reaction, first we are using mCPBA. It will attack on this alkene and convert it into epoxide. Then we are using BF3. It is a Lewis acid. So the lone pair of electron of oxygen will attack on BF3 and this will form. In the next step, one fluoride atom is removed and we have this compound. And in the next step, as we have positive charge on oxygen atom, so this oxygen is electron deficient, so this bond can break and this electron can shift from here to oxygen atom. One probability is that this electron can also shift, but shifting of these electrons leads to formation of this carbocation, which is more stable. In the next step, hydrogen atom is shifted here and we have positive charge on this carbon atom. In next step, the lone pair of electron of oxygen will be shifted to here to form a double bond and positive charge on oxygen atom. And in the next step, this bond break and the lone pair of electron will shift to oxygen and we have this as a final compound. So option D will be the correct answer. Next, in the next question, we are first using DIBAL. DIBAL is diisobutyl aluminum hydride. And it is a reducing agent and selectively used for lactones. That is a lactone. So it will reduce the carbonyl group of this lactone to OH. And then in the next step, the lone pair of electron of this oxygen will shift here and this bond will shift to this oxygen atom. So we have this compound. In next step, we are using Grignard reagent and it will attack on this carbonyl group and we have this compound. In next step, we are using PCC. PCC will oxidize these OH into ketones because they are secondary in nature. So the option A will be the correct answer. Next question is from CSIR net June 2013. We have reactant as well as product and you have to identify the appropriate sequence of this reaction. So we have 4 types of reagents here: MnO2, glycol, PCC and Jones reagent. Jones reagent, we know that it converts alcohol into acids, but in the product we don't have any acidic group. So options C and D are not correct. If we first use PCC, it will convert this OH group into ketone and this into aldehyde, and then it may undergo oxidative cyclization. So this cannot be the product. So first we will use MnO2 because MnO2 selectively oxidize the benzylic or allylic OH groups. So in the first step we are using MnO2. It will convert this OH group into ketone. MnO2 does not attack on alkenes, alkynes and saturated alcohols. So it is appropriate for this step. In next step we are using glycol. This glycol will convert this, will remove this oxygen atom and it will be attached to this carbon atom. In next step we can use PCC, and this PCC can convert this primary alcohol into aldehyde. So option A will be the correct answer. In next question we have cis-but-2-ene-1,4-diol and we are using these reagents. So we have to identify final product. Cis-but-2-ene-1,4-diol has this structure. So in the first step we are using methylene iodide, zinc copper couple in DCM. So this reaction is Simon-Smith reaction and it is the most common way of generating cyclopropane compounds. So it is basically transfer of carbene group. This CH2 group will transfer to this alkene group and it will try to attach in such a way that it is in the same phase of OH group. So we have this compound. So this carbene group is attached to this double bond and we have a cyclopropane group here. In next step we are using PCC in DCM. So PCC will can attack on any of this OH group. So first it will attack suppose on this OH group, primary OH group, and convert it into aldehyde. In next step it will undergo oxidative cyclization. So we have this cyclic compound here and finally we have this lactone compound. So the option A will be the correct answer, and the cyclopropane and OH are on the same phase and H will attach on same side. So they are above the plane. Next question, the major product of this reaction is asked. So in the first step, potassium hydride in THF will attack on this compound. Bn is benzylic group. So when we are using potassium hydride, it is a strong base and we have beta hydroxy trimethylsilane here. This is the alpha carbon beta and OH group on beta carbon. So beta hydroxysilane. So when we are using potassium hydride, it will remove Me3SiOH as trimethylsilanol. It will be removed from this compound and we have one double bond here, and this reaction is highly selective syn elimination. Syn elimination means we can use only this OH group. We cannot use this OH group because it is below the plane and SiMe3 is above the plane. So the OH group and SiMe3 should be in the same plane to be removed from the compound. So we have one double bond here. In next step we are using mCPBA and it will undergo epoxidation and oxygen atom will attach on the same side to that of OH. We have discussed it previously. Generally oxygen atom of epoxide try to attach on the side which is less hindered, but when we have OH group in the compound, then it will attach on the same side because it can undergo hydrogen bonding. So the option A will be the correct answer. Next question is from CSIR NET December 2014 and the major product of following reaction is asked. So in the first step we are using zinc ACOH. So this zinc will remove bromine atom. So we have two bromine atom, but it preferentially removes or selectively removes bromine atom close to carbonyl group. So this bromine atom will be removed. In next step, we are using PHSE-Na. So because sodium is electron donating in nature, so these electron will be shift to Se and it will be negatively charged. So it can attack on this carbon and this Br minus is removed. So we have this compound. In next step, we are using mCPBA, and we have discussed previously that mCPBA can convert selenium and sulfur compounds into sulfoxides and sulfones and selenoxides and selenols. So it will first convert it into selenoxide, and in the next step, the beta hydrogen atom, this bond will break and this bond will shift to selenium, and this O minus will attack to H. So it will be removed as PHSeOH, and we have one double bond here. So this will be the final compound. In next question is from CSIR NET December 2015. So in the first step, we are using PHCOOH in DCC, DMAP in DCM. DMAP is dimethylamine pyridine and it is acylating agent. We are using PHCOOH as acylating group. So this PHCOO will attack on this OH group, and in next step we are using pyridine dichromate in DCM. So it will convert this OH into ketone. This is a secondary alcohol, so it will be converted into ketone. In next step, we are using alumina. Alumina causes beta elimination of hydrogen atom. So this is the alpha carbon atom and this is beta. So hydrogen attached to this carbon is removed and this bond will shift here. And this bond will shift here and PHCOO group is removed. So we have this as a final compound. Next question is from GATE 2017. For the following three alkenes, the rate of hydrogenation using Wilkinson catalyst at 25 degrees centigrade vary in the order. So we have three alkenes here and we have discussed it in the Wilkinson catalyst video that this is the preferential order of the hydrogenation of alkenes. Because Wilkinson catalyst is highly hindered molecule, so it can attach easily with the alkenes which are less sterically hindered. So primary alkenes can easily hydrogenated as compared to more substituted alkenes. So in the series, first we have cyclohexene and next we have disubstituted trans alkene. So option second, and option 3 is the alkene with 3 substitution. The rate of hydrogenation for it will be list for this reaction. So 1, 2, 3. The option B will be the correct answer. The next question is also from GATE 2017. In the first step, we have secondary amine and this carbonyl group. So this is the enamine reaction. And we have enamine here, and enamine are nucleophilic compounds, so it can attack on this carbon atom of this compound and this bromine atom is removed. So we have this, when this bromine is removed, the positive charge will shift to this carbon atom and this can attach to enamine here to form compound. And another possibility is that this double bond shift here and we have positive charge on this carbon atom and enamine can attack on this carbon atom. So using first carbon cation we can have this product, and using second carbocation we can have this product. When we do hydrolysis of it, it will convert into it and it will convert into this. So option B and D are both are the correct answers. In this reaction, pyridine is attacked by pyracid. So it will convert into pyridine and oxide. And in the next step, we are using benzyl bromide. So this electron-rich oxygen will attack on this carbon atom. This bromide is Br minus is removed from the compound. So we have this compound. In next step, we are using NaOH. So OH will attack on one of these hydrogen atoms and this bond will shift here and this bond will shift to electron deficient nitrogen atom. So we have benzaldehyde and pyridine as final compound. So option D will be the correct answer. The next question is from GATE 2018. And in the first step, we are using LDA. So LDA will remove alpha hydrogen atom and it preferentially attacks on the less substituted carbon. So hydrogen atom is removed from this carbon atom. And in the next step, we are using PHSCCl. So this electron-rich carbon will attack on selenium and it is attached to this carbon atom. In next step, we are using hydrogen peroxide and hydrogen peroxide functions similar to mCPBA because it is also upper acid. So it will convert this selenium compound into selenoxide. In next step, the bond of this beta hydrogen will shift here and this bond will shift to selenium, and in next step this O will attack on H. So it is removed as PeSeOH and so this will be the final compound. So option B is the correct answer. The next question is from GATE 2019. So we have to identify P and Q. We are using peracids. So these peracids will attack on alkene group and it convert it into epoxide. But when we have R as H, so this will become OH. And we know that when we have OH group, epoxide oxygen oxygen atom try to attach on the same phase of that of OH. So it can undergo hydrogen bonding. So the option B or C can be the correct answer. But when we are using COET group as R, so it will become ester and the oxygen atom try to attach in such a way that it is away from the sterically hindered group. So if the OCOET group is above the plane, then it will undergo below the plane. So the option B will be the correct answer. So thank you so much for watching my video. Please subscribe my channel and press the bell icon for future notifications and share it with your friends.